This conference will now be recorded.
Okay, yeah, so when we are talking nowadays about disordered systems in statistical mechanics, this means actually a large body of topics. But initially, the subject itself emerged from the fact that in real life materials, you will have impurities, you will have some, if you want, some disorder in materials. So this means that all materials to some extent will be more or less disordered. And the question is then to understand whether this disorder, these impurities, are important to characterize the macroscopic behaviors of the system. And in particular, one may wonder whether they would affect phase transitions that we usually characterize in the context of standard statistical mechanics, as you know, when you study Ising systems, for instance, or second-order phase transitions, as you have been studying during the first part of this course. So I will start actually by giving you some concrete examples of disordered systems. Yeah, I should encourage you to stop me and ask me questions if this is unclear or if there is something unreadable or unclear on the blackboard, which might happen, of course. So let me just list a couple of examples. A first example that which is quite natural is the problem of disordered conductors. Okay, so you take a metal, and you know that typically if you have a perfect metal, then the conductivity will be given by the Drude model, which is a relatively trustful model. And one may wonder what happens if you include disorder in these systems. And this somehow is related to the lectures that some of you might follow by Christophe Texier, for instance. And that has been a subject of wide interest in the last decades. Another class of problems that people have studied a lot in the context of disordered systems is what I would like to call elastic manifolds, or say elastic line in a disordered medium. So what do I mean by that? Well, if you just take an elastic line and if you just take in on a clean system, well, typically it will tend to be quite flat to just minimize its energy. Now, on the other hand, if you impose for some reason that this line has to go through some impurities through the system, which are some kind of pinning centers, you can think of this as some kind of pinning centers. And you assume that you have a line, say that starts from here, an elastic line, and which is directed. So, and in order to minimize its energy, it would have, say, to go through all these impurities. Okay, and this has typically many applications. For instance, you might think of this as being an interface between up spins and down spins in an Ising model, for instance. Okay, think of plus spins there and minus spins there, and you could assume that, for instance, there are some non-magnetic impurities along the line on this material, such that your interface will preferably pass through these points, and that can be an example of such a problem. You might think of it. For those of you who are more inclined to solid-state physics, you might think of it as, for instance, as a flux line in a disordered high TC superconductor, where you impose an external magnetic field, and if you assume that there are some impurities in your sample, which will always be the case, then the vortex lines will be pinned by these pinning centers. Superconductors. This might be also a contact line in some wetting experiments, and so on and so forth. So there are actually a wide variety of systems which are, which can be described by this kind of elastic systems in the presence of a disordered potential. And again, this has been widely studied in the past, in the recent past, and maybe some of you are actually following the lectures by Wiese and Camille Aron, where they actually also discuss these kind of things. So I am actually starting with these examples because basically, I mean, these are the ones that I will not touch too much upon, that we will not touch too much upon during the lectures. But nevertheless, this is useful to mention them. Now, closer to the subject that we will start to study is the problem of structural glasses. Okay, so if you look at the glasses, sorry. Yeah, can you mute? Excuse me, can you mute, please? Matteo, I think that
yes, it's
your
me.
microphone.
Sorry.
Except if you want to ask a question, of course. So, and this is basically, this has to do with the glasses that you can see in the windows that we have around. And the idea is that some liquids, under some circumstances, when you just cool down rapidly, then basically they form this kind of amorphous systems where you still have a kind of solid order because the glass is solid, but on the other hand, there is no crystalline order in the glass, right? So these are kinds of amorphous solids. Which are also part of the realm of what we usually nowadays call disordered systems. Now, of course, we want to have some models to look at, and maybe it's already nice to look at one of the prototype models that we will study during this set of lectures, which are disordered spin systems. Okay, so what we want to study are basically, Ising type of models that you know very well. So if you have a pure model, so usually we talk about pure model to talk about the models that we have been studying so far, that you have been studying so far. So for instance, you might think of Ising, so a pure Ising model, which you would define on ZD for instance, or any type of graph, and you would have say a Hamiltonian, which said sort of generically would read like that. So you would have an interaction between nearest neighbors, and you might have an external magnetic field coupled to these spins. Okay, so you have Ising variables, which are just plus minus one. So that's the situation. That's what I would call a pure model. Now, what happens if you introduce some kind of disorder? So, for instance, you might think of this model that I just drew upstairs, where you have this interface between, say, plus spins domains and down spin domains. Because of these impurities, because you might have some non-magnetic impurities in your system, it might be that this J here will itself be quite inhomogeneous. That means it will depend on I and J, and in some cases, this might even become a random variable, and that's what we will basically. So this Jij might become random, and that's a case that we usually call random bond model for some obvious reason. It might be also that the H itself might become heterogeneous and might depend on the lattice site and might even be itself a random variable. So the H that you have here might actually become Hi and become, in this case, a random field model. And we will come later to that kind of models, they display different behaviors depending on random bond and random fields. But that's kind of the prototypical model that we would like to study. Maybe a last example to finish this list, which is of course far from being exhaustive, which is what I would like to mention, or to call like heteropolymers. You might, for instance, just think about ADN, say DNA, sorry. And so typically the picture that you would have in mind is that, okay, so you will have your DNA brain, or that might be another kind of polymer anyway. And it might be that you have these bonds there, which are in this case, so you might have these kind of things, ATCG, for instance, and again, the same thing here. So these bonds here might be close, for instance, and that in these regions, you might have these three kind of bases. And again, in this case, you have also a kind of disorder in the disordered configuration in the following sense that the positions of these molecules here, either A or T, are fixed along the chain, but their position might actually fluctuate. So in fact, so that means that essentially the labeling along the line is fixed, but the positions of this guy then might be here or might be there or whatever, and that means that it might indeed interfere or interact with other types of molecules in the following. So again, that means that you have a pretty much heterogeneous structure, and that plays the role of a kind of disorder that we would like to study in this course. Now, if I want to have a kind of common description of these different models at this stage, at least, what is important to understand right from the beginning is that we are actually dealing in all these systems with two kinds of different degrees of freedom. And I will find useful to discuss, say, the model of H of the Ising system in the presence of bond disorder. So just to fix the idea, I will just define and introduce a notation of this H, which basically depends on two sets of variables. And I will just forget about the random field for the moment, just for the sake of discussion. So in all these systems, it turns out that we have actually two sets of distinct variables. The one that I've denoted by sigma, which are the spins, and the other ones, which are the J, which are the couplings. And they are actually extremely different in the following sense. So the thing that we have to keep in mind is that on the time scale of the experiments, on the time scale of the observation time that we have in mind, on this time scale, we have to have in mind that basically the sigma i's are kind of fast variables in the sense that the spins themselves would be able to equilibrate in the thermodynamic sense. So one might be able to describe them in the context of the equilibrium standard statistical mechanics. So the sigma i's, they will actually be called we would say that they are thermal or even dynamical variables, in the sense that they may indeed flip quite fast. So the spins that we are talking about here, or the one that I just erased there, maybe it was nice to have this picture again. So essentially, the spins, so that means that the positions, if you want here, of this interface would be able to move and fluctuate. And these are the equivalent of the spin variables in this setup. On the other hand, at variance with the sigmas, which are fast variables, you have the j's, which are which are first random, but on top of that, these are random variables which are not thermalized, in the sense that on the time scale of the experiments, these jij essentially are frozen. Okay, so this j, so at variance with the ones with the sigmas, which are thermal, dynamical, and fast variables, the j's are frozen, in the sense that, so this, in this language here, they would describe the positions of the impurities. These impurities are present in the material, and they will not move during the time scale of the experiments. Okay, so that means that they are there, they are really frozen, and it would take a huge amount of time for them really to thermalize. And this time that they need to thermalize is much larger than the one on which you are observing it. And so they are slow variables, and the word that we will use to qualify them is we will usually talk about quenched variables. That means that on the time scale of the experiments, these j's basically will not move at all. Okay, so in other words, you immediately see that you have two sources of randomness. That means we have two levels, if you want, of randomness or probability measures, one associated to the sigmas, and the second one associated to, so levels here is a bit of a vague name, but we have two levels of randomness, and I need now to introduce some notations to essentially discuss average over the sigmas and average over the j's. Okay, so let me just introduce the first guy, which I discussed. So that will be essentially a first probability distribution P of sigma, keeping J fixed, which I would just write as 1 over Z, which will then depend generically. So this is my partition function, and then I have my Boltzmann weight, of course. Okay, so given the J, so if you want, it's a conditional probability in some sense. So given the J's, I give you this Boltzmann measure, and that's reasonable to assume that because the sigmas are still rapid variables and they will indeed thermalize. And that means that these are computed at 6J. And that the notation that I will use is that when I will compute an observable with respect, the average of some observable, say O, which might depend, say, on sigma and J generically, I will denote this as this notation here. Okay, so bracket index J, and eventually I will have to do some average over the random variables J, and in that purpose, when I will denote, to denote such kind of averages, I will actually use this notation. So expectation values, as mathematician would, which of course does not depend anymore on J. But the point is that the probability measure that you might have on the J's here is not necessarily given by statistical mechanics, by the Boltzmann weight, simply because these degrees of freedom have not thermalized. Okay, so that's really, really important to have in mind, that in all what follows, we will deal with these two kinds of degrees of freedom, and we will see how important it is to treat them separately in a correct way. And if you don't do that properly, you will see that you might obtain some crazy results. So that's really what the the statistical mechanics have to do about, which is how to deal with this kind of two types of random variables. Are there any questions? Okay. So now let me start with and enter into the details of one of the models, and that will be, if you want, one of the prototypical model that we will study at least in the first lectures, which are called Spinglass models. Okay, I'm sure that many of you have probably heard about it, and that's what I will start with. It turns out that these models, of course, were initially studied in physics for the reasons that I tried to explain, but during the last decades, they have been used in a wide variety of contexts, that goes much beyond statistical physics and physics in general. And so it has very nice interdisciplinary applications that you might hear about in other lectures as well. So let me start with some kind of phenomenology just to connect this model with, these models that I want to study, or that I have discussed before. So the first experiments were carried out in the 70s by people who were studying some magnetic alloys. And typically, they were looking at these cuprate manganate, copper manganate, manganese, sorry, alloy. And of course, the interesting thing, of course, maybe you don't know it, but the important thing here is that the copper atoms actually do carry a magnetic moment. So they are actually, sorry, the manganese, sorry, are actually magnetic, so they do carry a magnetic moment, while these copper atoms actually are non-magnetic. Now, what happens? How does such an alloy look like? Well, basically, if you are at very high temperature, this is just a completely, it's a kind of liquid state. And what people usually did, and in particular in the context of metallurgy, what people usually do to create such kind of alloy is that they suddenly cool down the system from a high temperature to a low temperature phase, and they do perform what is called a quench from high T to low temperature. And quench means that this is a rapid quench, okay? So that's the word that I should add here, which implies that when you start from a completely disordered liquid system, and when you suddenly quench it, well, basically what happens is that the positions of these atoms will be stuck forever. They will be just quenched in the exact sense that I described before, so that if you look at the configurations of these atoms, so basically you would observe something like that. Okay, so the positions of these atoms will be quite disordered, in fact, and you will have. Okay, I know that using the color usually on the board is quite bad here. With the camera, but what will happen is that you will have a mixture, since this is an alloy. You will have a mixture of manganese atoms. Say these guys will be manganese. This one will be some kind of manganese, but not necessarily up. It could be down. And there, okay, you could have also manganese there. But on the other places, you will have these copper atoms, which first are non-magnetic. So that means that they will somehow screen the interactions between these magnetic moments. And on top of that, as I said, because of this rapid quench, their positions is fixed. Their positions are completely fixed in the sense that they are quenched. Okay, so the positions of the atoms are frozen. They might equilibrate, but on kind of geological time scale, right? So that means that you would need a huge amount of time to see these guys indeed thermalize. So the positions are just frozen. They are quenched again. So that's what I meant before by quenched. But the spins themselves, they actually are free to flip. Okay. Are free to flip. Okay, so these are your thermal variables. Okay, so they are thermals. Now, what people so they started to make some nice and beautiful experiments on these systems, and they started to observe some kind of quite peculiar behavior from the magnetic point of view, and therefore people started to study this. To study the statistical physics of this system. So how can one describe this system? So as I said, you will have here these magnetic moments which will interact basically through a kind of interaction of the type minus j, ij, sigma I, sigma j, and the gij. So if I call this I here, the j there. So the interaction strength will actually depend on the distance between these two guys. And as I said, there will be these interactions will be mediated and screened via the presence, because of the presence of these copper atoms. So if you look at the interactions between the effective interactions, maybe it's nice to, I guess I can just write it here. If this is fine. Can you write that? Would like to have it on the same board as this guy. So you will have a kind of effective interactions between these spins. That means that again, you would like to have a model which will be of that form. Roughly speaking, where I and J are just labels for the atoms, and as I said, this Gij will be some function of J, but as I said, would be only a function of the distance between Ri and Rj. Okay, this really requires to have some microscopic model to study that, but people have done that. I will not reproduce these computations. And if you plot this G of R as a function of R, what you can show, and this was shown actually by these four guys, Ruderman, Kittel, Kuzuya, Yoshida. So this is now quite well known under the name of RKKY interaction. If you plot this J of R as a function of R, then you will see this kind of damped oscillations. So there are two things to notice here. First, that the amplitudes of these oscillations indeed decays to zero as R goes to infinity, which is expected. But what is less expected is that the J's here may be positive or negative. So you see that depending on the relative positions of these guys, of these two guys, the effective interaction might be ferromagnetic or anti-ferromagnetic. And that actually creates quite some problem here. So J actually, so that means that Jij can be positive or negative.
Quick question.
Yeah, please.
In the Hamiltonian, you take a nearest neighbor interaction. So.
Oh yes, you're right. Yeah, this is not really correct.
Okay.
Yeah, I mean, okay. Yeah, this is in principle here. You might sum over all the pairs ij. I mean, for the model that I have in mind. Yes. Thank you. Yeah, that's a good point. I will come back to that in a minute. Thank you. So, indeed, and that's an important point. Now, the fact that this might be positive or negative actually creates or gives rise to interesting phenomenon, and in particular, this gives to some frustration in your model. So maybe one remark that one can do at this stage is that basically you see that this Jij here has this structure, but on the other hand, since the positions of these I and j are kind of random, eventually this is very close to a model where you would somehow fix the I and j and take this Gij as a random variable. Okay, I will come to that in a minute. But the important fact indeed is that this Jij can be positive or negative, and this effect here, this fact, might create. So this is implied by that what we call frustration, and that's a very important effect feature of these Spinglass models. Indeed, and this can be seen by just looking at the ground state of your system. So you see, if you suppose that the Jij they can be random, but suppose that they are all positive, well then it's clear that the ground state will be such that essentially all the spins will be up or all the spins will be down, and basically that means that you can easily find the ground state of your system, even though you have some disorder. If you have only ferromagnetic interactions, life is still simple. Now, if you start to have some positive and negative type of interactions, you might have frustration, and this can be seen on a very simple example. Imagine that you put your spins on some triangular plaquette, so on some triangular lattice. So imagine that you have somewhere in your lattice some kind of things like that, which might be connected to. So suppose that you put your system on a triangular lattice. This is just to fix the idea, and assume that you have here a j which is positive. So here it will be positive. Suppose that here it's negative, so that my example works. And suppose that this one is positive. So if you are very naive and you are looking at just Ising spin, so you start with one that would be plus. In any case, you would have some kind of Z2 symmetry, so plus minus. Now, if this one is up, because the interaction is very negative, then you would like to have a spin which is down. Okay. Now, on the other hand, if this guy is positive, then you would like to have this guy to be also positive. But then if you do that, it's clear that you are not able to optimize this last bond because this bond is positive, and it would naturally or naively require to have the spins aligned while they are anti-aligned. So that means that the structure of the ground state will be much more complicated. I'm not saying that the ground state does not exist. I'm just saying that the ground state will be more complicated first, and on the other hand, typically it will have a huge degeneracy. That means that you will have a huge amount of configurations which have an energy which is very close to the ground state. Okay, so that's what I want to illustrate here on a very simple example. So this frustration will lead to complicated ground states, and in general, this will lead to a huge degeneracy, or in other words, the entropy associated to the ground states or to the low-lying states will be quite high. Okay. So that's the kind of things that that people have observed. Now, what else can we say? Well, we can try to see what happens if we talk about a transition, the existence of a transition in this model. So, and I would like just to say a word about the Spinglass transition, at least at a very phenomenological level, and we will come to these points in greater details later, of course. But I want to say something about what is, I mean, just to try to give you the flavor that there might be some kind of interesting phases in this model. So again, I have this kind of model in mind. And if I look at very high temperature, well, then you can see what will happen, or say the entropy will win in the sense that the spins will flip up and down, and essentially the configurations up will have the same probability of the down configurations, and therefore you will have a kind of standard paramagnetic phase, exactly as you know, in the sense that if I look at, so what I want to mean by that is that if I look at the average of sigma I for a given J, now of course this guy, you see, the important point is that the local magnetization will fluctuate from site to site, of course, right? Because you have broken the translational invariance in your system. But nevertheless, in this case, if you look at what happens at high temperature, well, basically the sigma I will be 0 for all I. Okay, so the spins again will flip up and down. Well, on the other hand, if you are looking at low temperature, if you are, again, imagine that you are at very low temperature, then it's clear that the spins, they will be frozen, okay? And they will be frozen in the state which basically minimize the Hamiltonian, so the energy of the system for a fixed configuration of J. So in other words, that means that there will be some sites I where the spins are up, and there might be some site J, sorry. So on average, it would be positive, while for some other guys, on average, it would be negative. Now, of course, if you do that, and if you naively, again, average over J, you will completely wash out this kind of order that might exist for a given configuration of the J. But so you see what happens is that there is some kind of order, because spins still might be frozen, so you might have, they might carry a local magnetization, but it's of course different for a ferromagnet in the sense that if you naively average again over J, then you will completely lose this order. So in that sense, you have some kind of order, but which is obviously different from a ferromagnet, because from a pure ferromagnet, right? Because again, as I said, if you really look at this quantity here, and if you further take the average over the J's, then obviously this guy, because J's typically will be positive or negative with the same kind of probabilities, and then this quantity will again be 0. So that means that you have a kind of order, but this order is different for ferromagnet, and later on we will try to understand what is the good order parameter for this transition. But what I want to say is that roughly speaking, the behavior that one expects is in some sense similar to a glass, because a glass indeed has some, is a solid. So in some sense, it has some order like a solid would have, but nevertheless, it doesn't have a crystalline structure because it's amorphous. And that's why, in that sense, they are qualitatively close to a glass, and that's why they were called spin glass. Now it turns out that this analogy goes much beyond that, and during the last 20 years, people have actually understood that the models developed for spin glasses, mean-field spin glasses in particular, as we will see, might be interesting for true glasses, but this is yet another story. So at this stage, I just wanted to let you, understand why we use this spin glass terminology. Is that clear? Right. So now, based on that, on these pictures that I tried to explain, people try to analyze some model. Now, as it was mentioned by one of you, the model that you would like to write from the microscopic description turns out to be quite complicated, because we have seen here that indeed, in principle, we have a sum here over all the I and j's. But on the other hand, we have seen that these j's, first, indeed, they are positive or negative, which is quite complicated. But on the other hand, we see that this falls off quite rapidly. In fact, this is essentially exponential. And that means that in reality, effectively, one spin will only interact with only a few neighbors and will not really see the others. So that led people, and the first model was actually devised and proposed by Sam Edwards and Anderson, Phil Anderson, that you might have heard about, which have, in principle, in particular, made great contributions to the problem of localization. Edwards also actually has done a lot of things in the context of polymer physics. But is it still okay? Can you see the blackboard? Because suddenly it became dark here, but you probably don't see it.
It's okay.
Okay. Okay, so let's go for some models. And indeed, the model that, which is somehow, which was the first model, is a model by Edward Anderson in '75. And the idea is that, okay, if we really want to take into account the model that I just erased below that, is slightly too complicated. And instead of that, let's try to come back to the Ising model that we like, which is usually defined on a lattice. So let's look at a model on ZD. But to take into account the fact that, so we will have spins on site I, okay? But to take into account the fact that we have these kind of interactions here, which might be positive or negative, then basically we will take in, and the fact also that it decays with distance. So that means that these spins will only interact with its nearest neighbors or few neighbors, and in the simplest case, to the nearest neighbors. So you will write your Hamiltonian H of sigma and j under this form, where now you really take a sum over the nearest neighbors, but to take into account the fact that you are now on a lattice, while the real model were kind of off lattice with some kind of disordered positions. These disordered positions, these random positions of the atoms, eventually translates itself into the randomness of the interactions, okay, which indeed might be positive or negative. So that means that this Gij, and that's the model that we usually study, so that's the Edward Anderson. So Gij are IID random variables. Okay. And these are random variable, and the randomness that you choose for these interactions then is a bit ad hoc. In the sense that in principle it does not need to be governed by any equilibrium statistical mechanics rules. And typically people have consider different kinds of disorder, but the most popular ones are simply the case where Gij are just plus j or minus j with some probability half and other probability. So that's one example where say Gij, you take it randomly to be say plus j with some probability with probability half, sorry, and minus j with the same probability. Another example that you can imagine is the case, and which is indeed usually simpler to treat, is the case where the Gijs are Gaussian random variables. Okay, so you might consider the case where Gij are centered Gaussian. And you may hope that the large-scale properties will not depend too much on the kind of disorder that you choose. So that's really the model that you would like to solve, and in particular, you would like to understand what happens, say, in d equals 2 or d equals 3. Even more interesting, d equals 3, of course. And it turns out that this model is very hard to compute. I mean, to study. There is no exact solution for it, except in 1D. But well, it is a bit trivial. But in higher D, I mean, the situation is still extremely debated, and this is nowadays still a problem of interest for research. Now, as you can imagine, because this model is too difficult in finite dimension, on a finite dimensional lattice, one of the first approximation that you can imagine is to perform a kind of mean field approximation of this Edwards-Anderson model and look at a mean field version of it. So that's when you start to do that, indeed, we will see that there exists a large variety of mean field models that we will discuss, in fact, at length during the first lectures. And the first model that I want to discuss is the so-called Charrington-Kirkpatrick model, which some of you have maybe heard about, and which is basically, so it was introduced in 1975, and that's a mean field. So that's a mean field version of Edwards-Anderson. Okay, so that's what I will usually call EA for this model. Mean field version of EA in what sense? Well, in the sense that instead of having a spin that interacts with only its nearest neighbors, you now take an interaction with all of the other spins. Okay, so instead of having an interaction on ZD, you have basically, you put your spins not on a square lattice, but on a graph, which is basically the fully connected graph. Okay, so that means that now the H of sigma and J, now the sum here is not restricted on the nearest neighbors, but it's really on all of them, and with I much less than J. And again, this Gij at the same kind of couplings. So that means that the spins. So then that means that it's like spins are now leave now, if you want, I should say, on what is called the fully connected graph. Okay, instead of ZD. So it's also quite different from the model that I initially stated, where with the true RKKY interactions, because I mean, in reality, the interactions really decay exponentially. Okay, so that's true that in the first model that I wrote, I had to write the sum over all the neighbors, as one of you mentioned, But of course, the j's at that time was a function which is decreasing as a function of the distance between Ri and Rj. Now here it's quite different because all of the spins you see, I mean, there is no distance. There is no notion of distance anymore in this model. Okay. Now, if you do that, of course, you might, if you have done this kind of mean field model already for pure Ising, you know that you need to choose the j's in a particular way. And in fact, okay, so we usually take the Gij's, of course, to be 0. I mean, exactly as we did here. But I would like to have the Gij's also as Gaussian, if you want. So, okay, maybe I should say here that we will take the Gij, of course, again, in this case, IID, Gaussian, random variables, which are centered. But now the variance, you need to scale it correctly such that you have a good thermodynamic limit. Okay, so suppose that you define this model on a fully connected graph, but the graph is not infinite. You have actually a finite number of spins. I mean, otherwise, I mean, at some point, you need to make your study with a finite n and eventually look at the thermodynamic large n limit. But I will just denote by n the number of spins. Okay, so I have n spins, which are all connected. And you would like this model to have a nice, well-defined, by nice, I mean well-defined thermodynamic limit. And if you do that, it requires a bit of work, which I have not time really to do here, but believe me, you need to have a variance which is itself, which scales, if you want, with n. So we will see that later when we will study other kinds of models, but basically, you need to scale it as a 1/n. Okay. This can be seen, for instance, as I mentioned in my notes. By the way, the notes are, you have access to the notes. They are handwritten, but I hope you can read them and maybe they help you to follow a little bit what I'm writing. You can indeed see, for instance, if you do a high temperature expansion, it is easily seen. Easily is a big word. You can see that this is required. Okay, so that's just that the limit when n goes to infinity is well defined. Okay, well, so that's one model. Now, what about this model and what? So this is called. So this one is the EA. This one, as you can imagine, is this SK model. Now, the SK model was actually solved in the 80s, and it was solved by Giorgio Parisi, who is the famous Italian theoretical physicist. And to do that, he introduced quite powerful and amazing method, which is called the Replica Method. And you will see in detail during the next lecture what this replica method is. It's a quite amazing method. And so that was already quite some time back. And this was, of course, non-rigorous in the sense that this is exact in the sense of theoretical physics. But only recently, means in 2006, some of these predictions were proven rigorously mathematically by a few mathematicians or mathematical physicists. I can maybe just mention a few names because essentially in 2006 and after, and there have been many people. I mean, first one was Guerra, and then Fabio Toninelli. And then more recently by the famous French mathematician Talagrand. And okay, this is still, of course, a subject of research here. Indeed, this kind of, it turns out that these mean field models have actually generated a lot of attention because it turns out that already at the mean field levels, these models are extremely hard, both technically and also conceptually, as you will see when you will deal with this replica method. But this led to a quite rich tools that then later on have been developed and used in other contexts. So maybe I should say that the Edwards-Anderson model is still under debate. There are various, I mean, yeah, it's clearly under debate. There are various schools, essentially the mean field schools, Italian school, I should say, almost, against somehow the finite dimensional community, which pretends that somehow it's not clear that the mean field approach gives the exact results for the Edwards-Anderson model, saying d = 3, and this has led, for instance, to the school, I mean, the groups of Daniel Fisher, David Hughes, etc., to develop this droplet model, which is also a fantastic tool, and so this is still an open and interesting question. Now, at this stage, we can be slightly more precise about the order parameter in the model. So at this stage, I will again mostly give definition, but just recall for a ferromagnet. Well, for a ferromagnet, what I really need to study in principle is really to study what happens if I look at, so if I have n spins, then I should look at this quantity, and of course I want to look at what happens in the limit when n goes to infinity. But of course, if I want to see something non-trivial, I need to put some kind of external field, small one, which will act either as an external boundary condition. And then once I have taken the limit n goes to infinity, I will just take the limit when h goes to 0, where this h here is just a kind of ordering external magnetic field. And this is my order parameter, and that is called m, right? So that's basically what is called the magnetization. And this m is a good order parameter for pure ferromagnet because m is non-zero below Tc and 0 above Tc. Okay, fine. So that typically depends on T. Now, as we already anticipated for a spin glass, well, we are a bit in a trouble here because m is 0, in fact, even in a ground state. Okay, so that means that, so m means once, I'm not writing it explicitly here, but once, as I said before, you average over the j's, these guys is 0 even in the ground state, and that's not certainly a good. That's certainly not a good option. But on the other hand, we have seen that sigma I itself, for a given configuration of the j's, might be non-zero, but it might be positive or negative. So maybe a good idea to look at is the sigma I squared, right? Because the sigma I average squared, then this guy indeed might be non-zero even after averaging over the j's, and that turns out to be the good object, and the good object for spin glass, the good order parameter, is what is called the overlap, Edwards-Anderson's overlap, EA overlap, which is denoted by QEA. So this is typically known under the name of the Edwards-Anderson order parameter. And as I said, this is just, so that's the word that will come out very frequently in the following. Okay, and this QEA, as I said, is just this quantity, right? So this is just Okay. So again, exactly as we did before. So this is just the limit when n goes to infinity of this 1 over n roughly. Okay. Now, if you want to observe something which is non-zero, you need to apply, as we usually do for pure ferromagnet, you need to apply the equivalent of a magnetic field. At this stage, I will call it epsilon. I will not define it, but I just want to stress that this plays the role of a magnetic field with respect to the overlap, exactly as the magnetic field plays with the magnetization itself. Okay, so epsilon is not defined here, but it's just introduced here as a kind of symmetry breaking parameter. Okay. So let's be a little bit more precise by noting that, this is
just a quick question. Is it the square of the average or the average of the square?
Yeah, no, this is indeed the square of the average. Okay. Yeah, because sigma I squared in any case is just equal to 1, so the average of sigma I. Okay. Fine. So now, why is this quantity interesting? And let's try to understand it maybe a little bit better. So the expectation, of course, here you remember is an expectation. So maybe I should write a j here. Sorry. So I do that for a fixed j, and then I take the average over the j's, and that's what I did. That's what I do. Now, maybe you can have a look at. It's interesting to look at what I mean by that. If you look at this quantity here, if I look at this average, if you want, this sigma I squared, by definition, well, you see that this is just this is for fixed j, so this would be just 1 over j, sum over sigma of sigma I, exponential of minus beta times the same thing, right? So times 1 over j, 1 over zj, times this sum here, sum over tau. Okay, I can just write it like this if you want. Sigma I, exponential of minus beta h. Okay, so this is just rewriting the things. Now, the trick is to realize that, of course, the sigma here is just a dummy variable, okay? So that means that this guy, I can also rewrite it as the sum. So I is fixed, of course, but sigma is just a dummy variable, okay? So I can just make a change of variable, writing like that. Okay. Now, in other words, that means that I can still write it this way. I can still write it as 1 over zg square. Now I have a double sum over two kinds of configurations, sigma and tau, of sigma I, tau I. And now I have, if you want, I have a generalized Boltzmann weight. So I hope it's readable. I didn't do any fancy things, but I just rewrote these things as a double sum over sigma and tau. So essentially now that means that I can view this sigma and tau, I can just view that as two copies of the realization of two copies of my system. So two different realizations of the spin configurations in a given J environment. Okay, so the J's are fixed. I just now take two copies, sigma and taus, and I compute this this quantity here. So it's a kind of scalar product, if you want, of these two configurations. And I can also, this is quite natural then to denote this as an overlap. Okay, so that's basically, that's why this overlap name comes from. And in other words, you can even write it as this sigma I squared so that means that I think it's quite important to understand this computation, because this is really what so that means that I can still write it this way, and where this average value here now is taken with respect to a weight which is given on several copies, namely here 2 copies of your system. Okay, so the probability weight is just 1 over zg squared times exponential minus beta h sigma beta h tau j. Now, just one comment at this stage. You see that for a fixed j, the sigma I and the tau I are just independent random variables. Okay, so all the sigmas and the taus are uncoupled here. Now, what you are interested in, of course, is to compute the average values of this quantity over j. But immediately you see that when you will start to take the average of this object here over j, so imagine that j are just Gaussian random variables, so you will just take the average with respect to exponential minus gi squared, make the integral over the gi's, then what will happen is that you will effectively couple the sigmas and the taus, because the sigmas here, so they actually interact via the j matrix, and the tau also interact with the same matrix. Okay, so they are indirectly correlated, and indeed, when you will take the average over the disorder, you will start to couple your different copies of your system. Okay, so the sigmas and the taus here, I want to, yes?
Small question, is it 1 over zj and then the whole thing squared, or is it j squared in your equation?
Oh, yeah, thank you. Yes. Yeah.
Okay.
Okay, so this is this one times this one. Yeah, thank you. So these copies here, so I want to think of sigma and taus are 2 copies of my system. And these copies, this is what I will call later replica. Okay, so I have replicated my system to perform such averages. Okay. Now it turns out that this Q, so that means that the object that you can then define is this Q sigma tau, and that's the object that we want really to look at, which is the average. So this is the overlap between the 2 replicas. It's a kind of scalar product, if you want, of 2 configurations. Okay. Note that this guy has not been averaged over anything. Okay. Now, you will see in the notes that this Q of sigma tau actually can be rewritten in terms of the Hamming distance, and it measures basically, well, you see, if Q is 1, that means that all the sigmas and taus are the same. So that means that you take two configurations of your systems, which are at equilibrium, and then you compute the overlap. Now, if it's very close to 1, that means that all the sigmas and taus are almost all the same, and Q will be close to 1. Now, on the other hand, if sigma and taus are completely decorrelated, then basically this Q will be close to 0. So that measures how far these configurations are in the space of configurations, and maybe you know the terms of Hamming distance, which is usually a way to characterize this distance. You can rewrite it in terms of that. Okay. Yeah, I'm running out a little bit. I'm running a little bit out of time. But I want to discuss further mean field models, and then we'll see how far we can go. So, so we have seen the Edwards-Anderson, we have seen the SK model. Now it turns out that there are other interesting mean field Spinglass models that we will encounter and study in the following, and I just want to discuss them. So the first family of models that we can define are called the P-spin models. Just some kind of variant, if you want, of the so after the SK model, right, people tried to study other kinds of models. Okay, so I had the SK, just recall it. This was a model where you have this kind of interaction between two bodies, sigma I and sigma J's. And another class of models, which is indexed by an integer, which is called the P-spin model. So what is the P-spin? I mean, basically, instead of having a single, interactions which is quadratic between the spins, you now have something slightly more complicated, and you have actually now P-spins that may interact between each other. Sigma I1, sigma I2, etc., sigma IP. So you have P-spins, so that's hence the name. So P is an integer, less than 2. And then you have a tensor. Instead of having a true rank 2 matrix, you will have a tensor. So tensor is just an object. Don't need to know in deeply what these tensors are. These are just, and again, they all interact. So they are Ising spins, and they do interact. So they are again defined on the fully connected lattice. Okay, so you have an interaction between all the P applets here. And again, these are Gaussian random variables. And to have a nice thermodynamic limit, you need to scale properly the variance as we did before. So again, just to remind you the terminology, right? So we have these sigmas, which are the rapid variables, dynamical variables, and the J's, which are the quenched Gaussian random variables. Let me just. So of course, all these models you see are slightly different. Nevertheless, they actually fall into, or they can be described in a relatively unified framework. And in particular, if we look at, so I'm just making a remark here. If you look at the SK model and the P-spin model, you can actually compute the correlation function if you want between the, you can compute, say, sigma and J, what I want to say, yeah. So suppose that you compute, you want to compute the 2-point correlation function for the energies of 2 different configurations. Okay, so you take 2 different replicas of your system, and you just, so of course, H will be a random variable here, which depends on sigma, and there will be, you will have 2 to the n random variables. Okay, so if you look at what I want to say is that if you look at H of X of sigma and J, okay, you can think about it as 2 to the n random variables. For a fixed J, right? So this means that the sigmas are just, you have n spins, and if you fix the J, then that's what you would get. Now, if you indeed compute in this case if you compute these guys, and if you really average it, say over the okay, let me do it this way. You really want to so you compute this the value, these guys, and then you average over the j's, and then you look at how it behaves when n goes to infinity. Well, it turns out that this is exactly equal in all these models here. You can again write it as n times some function of the overlap, and that means that this will be some function of your overlap q sigma and tau averaged over q, essentially. Okay, so that will be a function of the overlap q sigma and tau. Yeah, I'm sorry. I'm going too fast. Excuse me. Okay, I'm not averaging over the sigmas. Sorry. Okay, so I'm keeping sigma and tau fixed. Okay, and I just want to look at I'm taking an average over the j's, right? So again, I have these 2 to the n random variables. That's fine, and I'm just looking at this average over the j's. But sigma and tau will be fixed. And indeed, what I show is that what you can show, it's a computation, right? You need to compute the things, but what you can show is that in all these cases, you can write it as n times some function of the overlap, okay? Where sigma and tau is just these guys there, okay? So that's a common feature of all these functions, and j, of course, depends. That's a remark here. Depends on the model. Now, a very brutal kind of approximation is to assume that you might consider that the sigma and tau, or say the energy associated to sigma and the energy associated to tau, are just independent random variables. So that's a kind of extreme case. So one extreme case corresponds to the situation where this guy here is just a delta function of sigma and tau. And that's actually the what is called the random energy model. Okay, so that's one extreme example. And so one extremal case, if you want, is the situation where the correlations, so basically where you consider that the energies associated to sigma and j's are just uncorrelated. It's just n. Okay, so here you need to normalize, I mean, the model that there is a half n by 2 delta sigma and tau. So that's the model actually, which turns out to be very interesting. This is called the random energy model, which was introduced by Derrida. And this is called the REM, R-E-M, random energy model. And it turns out, it's not completely obvious, but it turns out that this corresponds to the p-spin model in the limit when p goes to infinity. I will not show that, but. Okay. Good. So I would like to finish with, well, by introducing a notion which we will come back to later on in much deeper details, which is the notion of self-averaging. Before that, I just want to mention so that this REM model, actually, this is the model that you will study with Francesco during the tutorial. Okay. It's a beautiful model which contains a lot of physics, a lot of the physics at the end of the glassy phases. And although it looks simple, right? It might look simple here. It contains actually a lot of very nice information and very nice features. Okay, so I'm now arriving here with this notion of self-averaging, which is a crucial notion. I wish I had slightly more time, but I will not give the proof of the statement. So that means that I will let you have a look at the proof in the notes. This is a rigorous proof, actually. So, and if you have questions, I will be happy to answer to them. But I want to discuss the main message. So what I want to show you and discuss with you is the fact that the free energy is a quantity which is self-averaging. So what does it mean? So the question is the following. As we said, if you look at the disordered system at a microscopic level, you will see that there is a lot of heterogeneity, and this means that at the microscopic level, if you take one sample of, I don't know, whatever, of a metal, or one other sample of the same metal, just cut it in half, and you look at the two halves, but in principle, they might look microscopically extremely different. That means that you may wonder what this could mean for the thermodynamic properties. Does this mean, for instance, that the free energy of one sample is very different from the free energy of the other one? Does it mean that if I look at the specific heat of one, will it be different from the other one? Well, that would be quite annoying, because it's also not exactly what you would expect from universality, and you would expect again that at a macroscopic level, the samples should, on the large scale, behave in a relatively similar way. So it turns out that this notion of universality of the macroscopic behavior is true, but this is actually due to the fact that in the thermodynamic limit, so if you look at the thermodynamic limit, physical observables such as the free energy, for instance. I mean, you know that once you have the free energy, in principle, by successive derivative with respect to this or that parameter, you can get the average of any other physical observable. So in the thermodynamic limit, such as the free energy, essentially do not fluctuate. Okay, so of course one has to be a little bit more precise, and let's take the example of the free energy. So how do you define the free energy? And let's try to understand a bit more precisely the statements that I did concerning the fluctuations of these quantities. So in principle, you have your Hamiltonian here, and from the Hamiltonian, you will define the partition function, which depends, say, on beta and j, okay? And that will be just this guy. Now, this quantity obviously will depend on j. But z itself is not the quantity that you are after, but what you want to have instead is the free energy, okay? Which is just 1 over beta log of z beta and j. So Fn, as you expect, this is the free energy, and the free energy will be extensive. Okay, so the free energy itself might have large fluctuations simply because it scales like the volume, but more interesting quantities are the free energy per unit volume. Of course, this is what you would expect to be universal, right? I mean, or to have less fluctuations. If you look at, it's clear that these quantities being extensive, what you really are after is the free energy. Okay, so this is the free energy, and this is the free energy per spin or per particle. Okay. And what is that? This is just 1 over n beta times the log. Right. So now this depends on J's, okay? And in general, if J's is a random variable, then this will induce some randomness on Fn. So in principle, Fn itself is a random variable. So, and that is indeed what you would expect. So that's what I had in mind before. So you take one sample of metal and another sample of the same metal. In principle, they will correspond to a different realization of the positions of the impurities and so on. So there will be random variables. So the question is, what is the distribution of this quantity? Okay. Now it turns out, so the question is whether you have a wide or large distribution of this quantity around the F, or whether instead you have a very narrow distribution of this quantity. So one way to represent this statement is just to look at the distribution, which I would call P of, say, Fn beta of J. So that's the probability, if you want, that this guy is equal to S as a function of S. Okay, so that is that clear what I mean? By this quantity?
Yes, at least for me.
Yes.
Okay.
Yes.
Okay, good. Fine. So if you do that, in all the models that we have, that means in all the models where we have short-range interactions, typically the Ising model that we have, then this guy the distribution happens to be extremely narrow around, so you might think that this is a kind of Gaussian around its average value, which I will call F index Q. I will comment on that. And what happens is that the width here has some width Wn goes to 0 as n goes to infinity. So eventually, in the true thermodynamic limit, this quantity actually becomes a delta function. And that's what we call self-averaging. That means that these are random variables whose distribution becomes a delta function around the minimum or the typical value in the large n limit. Okay. So that's what is called a self-averaging random variable. Now, the value that you get here, SQ, is just, what is that? So it's the average value of the log of this quantity. Okay, so that's minus 1 over n beta times expectation value of the log of Z. Okay. And I call this Q here, it is because, sorry, this is what we call the quenched average. Quenched average. So this is what this Q refers to. And in principle, this is different from what we call the annealed average, where instead of taking the expectation value of the log, you take the log of the expectation value. And this is what is called the annealed average. And in the later lectures, we will explore more this notion. So this is just a remark. There are two remarks that I want to do. First remark is that in general, the quenched average, as I defined here, so the quenched, well, this is called here the quenched free energy, is different from the annealed free energy. What is annealed, FA, and you will see that in the lecture, in the tutorial about the random energy model, which is the log of the expectation value of Z. Okay. And the reason behind that, and that's the second remark, you see, I mean, in principle, Z also is a random variable, okay? Now, if Z itself were a self-averaging random variable, then it would have a distribution which would be highly peaked like that. And if Z is self-averaging, then in principle, computing the log of its expectation value should be the same as the expectation value of the log. Okay. But it turns out that generically, Z itself is not a self-averaging random variable. That means that it has actually wide fluctuations with a width, Wn, which does not go to 0 when n goes to infinity. And that's the second remark, which explains the first one, in fact. And the reason for that, okay, so this is something that Francesco will explain in the next lecture, actually. This is because Z itself is not self-averaging. So Z is not a good variable in that sense. And if you want to say something about Z, well, you need to know all the cumulants of Z. I mean, all the higher moments of Z. So it's a much more much wilder fluctuating random variables. So in the notes on in my handwritten notes, in page 11 and 12, I give a proof of this statement. The proof is actually quite simple. It's also very standard. You may have a look at it. I will be happy to answer your questions, if any. And next time in the lecture, actually Francesco will start by commenting again on this non-self-averaging properties of the partition function Z, and then he will really explain in more detail the replica method for Spinglass models. And in the tutorial, the subject will be about this random energy model that I discussed, which is a model where basically you look at such partition function here, but the H here are just IID random variables. That means that for different sigmas here, the H are just independent random variables. And you will see that it has already some very nice features. Okay, I'm sorry. I mean, I took slightly more time, but I had also started a bit late. I will be happy to take questions.
I have one.
Please.
Is the fact that FA and FQ are different only true in the thermodynamic limits? Or, because I mean, if we are not in the thermodynamic limits, everything should
Yes.
be regular and it should be okay, no?
You mean between FA and FQ? Well, I mean in general, FA and FQ. You see, if you compute it for finite n, there will be different anyway, right? Because if you take any random variable, if you compute simply, I give you a random variable which can be I don't know, positive Gaussian, for instance, and if you look at the average value of log x, so x is this random variable. If you compute the average value of log x or the log of the average value of x, then clearly they will not coincide. So in fact, for finite n, you will always see some difference between the annealed and the quenched free energy. Now it might be that under some circumstances, basically when you are at high temperature, it might be that the quenched and the average free energy coincide, and typically they cease to coincide in the Spinglass phase. But for finite n, of course, they will always be different. Is that clear?
Thank you.
Okay.
Excuse me, just a small question. I've checked and I don't see the lecture notes on the file managing system. Are they on the Citadel?
Sorry. So which notes are you talking about? Sorry, the one of today?
Yes.
They are supposed to be on the Dropbox. I mean, not on the Dropbox, but there is.
Okay. On the someone just
yeah.
put it in the. Okay, thank
yes,
you.
they should. They are there.
Right. Okay. Thank you.
Okay. So again, don't hesitate to ask questions about them. Right. I mean, I will be happy to answer. Okay, I see some link. Maybe someone put the. I see. Okay, thank you, Antonin. Yeah, great. Okay. So yeah, so the tutorial will take place on Zoom. Okay. I'm sorry, we are a bit sorry to have to use both things, but I took this somehow the habitude here during the first semester to teach here. It's still a bit strange because this room is empty and it's much better when you are here. But still, I found it slightly more convenient than using the tablet. So if it's fine for you, I think I will continue for that. I will be happy, by the way, to hear about your comments. I mean, if it's not satisfying like that, I can also adapt a little bit. Was it? I mean, globally, was it okay? Oh, sorry, please.
It was very good, readable, just on the right bottom side of the blackboard. Sometimes the sun was shining there, and then it was difficult to read.
Okay, I see. So you mean on that side?
Exactly.
I see. Yeah. The problem. Yeah. Okay. Yeah. Okay. Let's see. I'll try to do that to make an effort last time. Maybe I think I could shut this the windows on the right, on the lateral ones, the lateral side. Okay. Okay. Thank you for your comments. Okay. So see you then.
Thank you. Bye bye.
Okay.
Thank you. Bye.
Bye.
Okay,
Thank you.
Bye bye.